Hello, this video emerges from a very dark place. During one of the years that I was teaching this course, I was using the personal response system to check whether or not the students were understanding what I was saying during the lectures. In one particular lecture, I was asking the students a simple question about the difference between mutually exclusive and independent events. I asked the students this question once and they got it wrong. I thus did as you were supposed to and repolled and they got it wrong once more. I thus left it and then returned to the question at the end of the lecture, at which point they got it wrong for a third time. I thus left the lecture enormously stressed and extremely worried, as this difference between mutually exclusive and independent events is foundational in probability theory and immensely important. In this video, I'm thus going to try and explain this distinction at length. Understanding this is not particularly difficult, but it is massively important, so please watch the video multiple times if you don't get it on the first time through. Our learning outcomes here are as follows. By the end of this video, I want you to be able to explain what it means when we state that two events are independent, and I want you to be able to explain what it means when we state that two random variables are independent. If we go back to the video on Venn diagrams, I stated that one of the easiest mistakes to make in probability theory involves the following equation, the inclusion-exclusion principles. In that video, we drew circles proportional to the probability that x equals x and the probability that y equals y, and noted that there is a finite region of overlap between these two circles. In other words, there is a finite probability that x can equal x and that y can equal y at the same time, and that is to say that both these statements can be true simultaneously. Consequently, if we try to calculate the probability that x equals x or y equals y by just adding the probability that capital X equals x to the probability that capital Y equals y, we double count the probability that x equals x and y equals y simultaneously. We thus need to subtract this term from the sum, and forgetting to subtract this term is often done and is an easy mistake to make. Now, the other common mistake to make is to assume that the probability that x equals x and y equals y can be calculated by multiplying the probability that capital X equals small x by the probability that capital Y equals small y. Again, this is not true in general. It is only true when the event that x equals x is independent of the event of y being equal to y. To understand what this word independence means, recall that we can write the probability that x equals x and y equals y as the product of a conditional probability and an absolute probability as shown here. Here we have the probability that capital X equals y, given that capital Y equals small y, multiplied by the probability that capital Y equals small y. Now, if you can play the term on the right-hand side, the extreme right of this equation, with the term on the extreme left, you find that the equality here implies that the probability that capital X, the conditional probability that capital X equals small x, given that capital Y equals small y, must be equal to the probability that capital X equals small x. In other words, the probability that x will equal x will be unaffected by the fact that capital Y is equal to small y. To be totally clear on this, let's compare this definition of independence and what it means for two events to be independent to what it means for two events to be mutually exclusive. If you remember the Venn diagram for mutually exclusive outcomes, it looked like this. There was zero overlap between the red circle corresponding to the capital X equals B outcome and the green circle corresponding to the capital X equals A outcome. The conditional probability that x would equal A given x equals B was thus equal to 0. In other words, if x was equal to B, it will most definitely not equal A. This is in many ways the polar opposite of independence. If two events at capital X equals A and capital X equal B are mutually exclusive, then x's being equal to B essentially prevents x's being equal to A. In other words, x's being equal to B has a massive effect on x's being equal to A. It most definitely does not have no effect, as it would if these two events were independent. Our Venn diagrams have been very useful for understanding the meanings of conditional probabilities, mutual exclusivity, and concurrency of events. The question now is, can we develop a similarly useful diagrammatic representation for what it means when we state that two events are independent? I think that you can by using a one-dimensional Venn diagram rather than a two-dimensional Venn diagram. In this diagram, I use a horizontal line of length 1 to represent the sample space omega as shown here. If I have some outcome from an experiment, which I'll call A, I can represent the probability of this event by drawing a subsection of the line with a length proportional to the probability of A as shown here. Now let's suppose that I have a second outcome from the experiment. I can draw a line segment with length proportional to the probability of B on this one-dimensional Venn diagram. Furthermore, as with the conventional two-dimensional Venn diagram, the overlap between these two line segments will be proportional to the probability of A and B's happening at the same time. Furthermore, the length of the overlapping region divided by the total length of the line segment labelled B will be equal to the conditional probability, the probability of A given B. Now a couple of questions for you. Firstly, what would our one-dimensional Venn diagram look like if the two events A and B were concurrent? Pause the video for a moment and take some time to draw the diagram. You should have drawn something like this, and remembered that concurrent means that the conditional probability, the probability of A given B, is equal to 1. Now what about if the two events are mutually exclusive? Pause the video for a moment and draw a representation. You should have drawn something like this, and remember that, of course, events A and B are mutually exclusive if the conditional probability, the probability of A given B, is equal to 0. Now, as a final test, draw a one-dimensional Venn diagram for an experiment that always gives one of 4 possible outcomes, which we'll call A, B, C, and D. The final result you get should look something like this. There is no overlap between any of the line segments, but the total length of all the line segments is equal to the total length of the line representing omega. Furthermore, if you remember from our previous videos, we can represent the outcome of an experiment that gives one from amongst a set of mutually exclusive outcomes using a random variable, only if these events are mutually exclusive. Hence, in this example, we can rename our events A, B, C, and D using a random variable capital X, which takes value 1 when A happens, value 2 when B happens, value 3 when C happens, and value 4 when D happens. Let's now turn to the question of how we can use the Venn diagram to represent what it means for events to be independent. We have a partition going along the horizontal line here, corresponding to a partition of the sample space by the random variable capital X. Let's now take a second random variable that partitions the sample space in a different way. Let's call this random variable y and state that it can have one of 3 possible values, 1, 2, or 3. For reasons that will become clear in a moment, we will draw a one-dimensional Venn diagram to represent this way of dividing up the sample space that is perpendicular to the one that we drew for the random variable capital X. Now, the key point here is that we can think of the area enclosed in the rectangle, shown here, as yet another representation of the sample space omega. Furthermore, we can draw shapes in this area to represent the probabilities of getting x equals 1 and y equals 1 simultaneously, and so on, as shown here. The simplest way we might do this is to draw a horizontal line starting at the upper edge of the y equals 1 line segment and a vertical line starting at the rightmost edge of the x equals 1 segment, as shown here. This would give us a rectangular area, and as with any Venn diagram, the area of this region would be somehow representative of a probability. in this case, the probability that x equals 1 and y equals 1 simultaneously. We know the edges of this area, however, because of the way that we constructed our one-dimensional Venn diagrams. So the base of this rectangle has a length that is proportional to the probability that capital X is equal to 1. The height of this rectangle has an area that is proportional to the probability that y equals 1 by contrast. As such, this area is equal to the probability that y equals 1 multiplied by the probability that x equals 1. This way, as such, when we represent this area in this way, we have that these two events, the probability that x equals 1 and the probability that y equals 1, must be independent. There was, however, no rule requiring that the lines that we drew to separate off the area for the probability that x equals 1 and probability that y equals 1 have to be horizontal and vertical. We just did that because that was convenient. They could be sloped as shown here. This gives us a way of representing two events, x equals 1 and y equals, and a way of representing two events, x equals 1 and y equals 1, that are no longer independent, as this shape does not have an area equal to the product of its base multiplied by its height. So the area here is not equal to the probability that x equals 1 multiplied by the probability that y equals 1. We can play even more with this construction if we consider a division of the whole sample space. Here we divide up the sample space into the 12 possible combinations we could have for the random variables capital X and capital Y. Notice that each of the rectangles in this figure has an area proportional to the probability that capital X equals small x multiplied by the probability that capital Y equals small y, which implies that for every single possible pair of values for small x and small y, the probability that capital X equals x and y equals small y is equal to the probability that capital X equals small x multiplied by the probability that capital Y equals small y. When we are in this situation, we state that the random variables capital X and capital Y are independent. Obviously though, just as in our previous example, we do not need to make these lines horizontal, and we could represent our probabilities using non-rectangular shapes. We would then have that the probability that capital X equals small x and capital Y equals small y is no longer equal to the probability that capital X equals small x multiplied by the probability that capital Y equals small y. Our variables would thus no longer be independent. In fact, the random variables are no longer independent if we simply move some of the lines separating our various rectangles as shown here. Anyway, I hope this picture has made it a little clearer what we mean by independent events and independent random variables, and that you now understand the distinction between events that are mutually exclusive and events that are independent. To summarize, two events A and B are independent if the conditional probability of A, given that B has already happened, is equal to the probability of A. In other words, two events A and B are independent if B's happening does not affect the probability that A will happen. Two random variables are independent, meanwhile, if the conditional probability that capital X equals I, given that capital Y equals J, is equal to the absolute probability that capital X equals I for all possible values of I and J. Thanks for watching.